Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to this new series on some important theorems and their corollaries from calculus. So today's discussion is going to be on the discrete theorem. This theorem is related to the limits of functions in calculus. So this theorem helps you a lot to calculate and too many scenarios where the functions satisfy the assumptions of this squeeze theorem. So let's see how the statement of this theorem look like. So it says that if you have three functions and that satisfy this particular inequality, so you have h, f and g. So you have a function f which is kind of sandwiched between h and g, or which is lying between h and g for all x in the interval containing a point A, except maybe, except possibly at C itself, what A itself, sorry. So what does this mean? I'm going to explain very shortly. Additionally, you should have this. Additionally, limit of function h at A is same as limit of function g at A. Let's say this is equal to L. So if you have three functions which satisfy this inequality, in other words, your f is lying between h and g, along with that, so it says that h and g, the functions in between these two functions, f is lying. So in other words, f is lying between g and h at all values of x in the interval containing A. So there is an interval around a point A. So on this interval you have this relation in functions f, g and h. Okay, and this might not be, this might not hold on this A. So these functions can satisfy this relation on this interval, but they might not satisfy this relation on this value A itself, but they will be satisfying here and here. If that's happening, and additionally the limit of h and g are same, then we have a conclusion. Then limit x goes to A of f of x also exists, and the value of the limit is same as the value of limit for the functions h and g. So what does this say? I'm shortly explaining in a picture. So it says that if you have three functions, let me sketch a rough idea for this. Suppose you have three functions. Let's say you have a function, let's first settle some point A. Now suppose you have a function that is h in this way, okay, and then let's say you have got another function that is g, so let's say this is g, and you have got a third function. Let me call that third function as, okay, so f. So what is happening? So let me label all of these. So that's my function g of x, and this is my function h of x, and this is my function f of x. So what is happening? So like this is my value A. So around A if I settle an interval around a, near a, so what is going on around a? So the function f is between g and h. Then this relation might not hold on this at this point. So this might not hold. Like this relation cannot have true value at this point. So you can say that like this might not hold. G of x might not be less than equal to f of x, might not be h of x at x equal to a. This might not hold at a, but it should hold near a, like in the interval. There should be an interval over which this relation should hold. Even if it doesn't hold at a, but it holds around a small interval of a, around a there is a small interval over which this relation holds, then what happens? Then the limit of f is going to be whatever the limit of h and g. So like if limit of x goes to a at g of x is equal to limit x goes to a of kind of h of x, which is L, then limit of f is also going to be equal to L, which you can see from this rough sketch. That's my y and that's my x. So like if f is between two functions and the limit of these functions h and g, then the limit of f. So let's see some examples. One of the very famous examples you can find from here. So if you consider a unit circle, then like then you can define two triangles, like this triangle and this small triangle, this way, this triangle over here, the largest one, and then you can also define another triangle, smaller one, like this. Okay, so this one, which is given here, and this sector. So you can partition a certain area over here in this way. You can find three different geometrical figures. One is a larger triangle, and the other is sector, and the third one is the smaller triangle. So this is sector. So like one big triangle, and then inside that a sector, and inside that a triangle. So you have got these three geometrical shapes. So from these three geometrical shapes, you can find out this relationship: cos of x is less than equal to sine of x by x, which is less than equal to 1. And now you can see that when you see, if you define h of x equal to cos x and g of x equal to 1, then you can see that limit x goes to 0 of h of x, I mean the limit of this cos as 0 is going to be 1, and the limit of g at 0 is also 1. You can see because it's a constant function. So if the limit of the exterior these functions is same, then probably this limit is going to be the same. So in this way you conclude that the limit of this by sandwich theorem or by squeeze theorem, that limit of sine x over x at 0 is going to be also 1. So you might have seen this very beautiful result in your textbook. So it can be proved this way. So that was a sketch. That was not all the working. You can find too many other examples from the squeeze theorem. Let me do another example. Okay. So let's solve this question. So it says that calculate the limit of the function when x approaches to 0, and it doesn't give you function, but it says that your function is lying between these two functions. Additionally, the relation holds near the 0. You can say that it's holding near 0, interval 0. So you just need to define two functions. So h of x, let's say, is 4 minus x square, and say g of x is equal to 4 plus x square. So if I compute this limit at x goes to 0, for h of x, you can easily calculate that this limit is 4, and you can calculate limit for this g at 0. You just need to substitute, it is 4. So because the limit of the exterior these two functions agree, so therefore we can conclude by using the squeeze theorem that limit of the function f of x at 0 is also going to be 4. You can be asked to calculate, or can be said to determine this limit x goes to 0 of x times sine of 1 over x. You can directly substitute this limit, so like if x is 0, then sine of 1 by 0, so it's a troublemaking thing because sine of 1 by x doesn't exist, so like it's a troublemaking. So for that kind of perspective, we can use this squeeze theorem here. Let me show you the trick. So you can easily see that the function x times sine of 1 by x is lying between absolute of x and minus times absolute of x. Let me show you the graph. So let's plot minus absolute of x, then let's plot plus absolute of x, then let me plot x times sine of 1 by x. Oh, you can see that your green, which is x times sine 1 by x, is lying between absolute of x, this blue functions graph, and this red, in other words minus absolute of x. So we are sure that this x times sine of 1 by x is lying between absolute of x and minus absolute of x, and hence we can apply squeeze theorem, because this relation holds at least near 0. For our assumptions, it should hold near this point 0. So let's go and compute. Now you just need to define some function h of x, which is minus absolute of x, and the function g of x, which is absolute of x. So you can see that limit x goes to 0 of this h of x, this is 0, because this absolute function is continuous, and at 0 it has limit 0. You can also compute the limit of g of x, which is also 0. So hence you can say by squeeze theorem, you can say that this limit x goes to 0 of x times sine of 1 by x is also 0. In fact, you can use this strategy to answer too many other questions. So far so good. Thank you.